Hello, Mr. Aaron, Mr. Ryan. How are you today?
Good.
Today, yesterday we talked about the hashing function. The hashing function allows us to map arbitrary large data x. Yeah, this could be any size into a fixed size, which could be 32-bit integer. Yeah. So why we use the hashing function? Because we need a hashing function to compute the location of the values to be stored. So basically, the hash table is a fixed size, right? It's a fixed size. And then we calculate the data hashing function of the data, and it gives us a value, so it tells us where to put it. If there are conflicts, what it means that if there are two different kind of data, if x not equals to y, and if hx equals to hy, that means a conflict because we have different data, different inputs, but the hash function gives us the same value. And what it means that these two values x, y will be pointed both to the same location, and we can use the linked list or a list. Yeah, and we generally don't want this to happen as much as often, because when this happens, it means that it will be slowed down, right? There will be a performance degrade. Yeah, because we take O(n) time, linear time, to go through a linked list or a list to find out if the element is in a list, right? Yeah, we want the data to be geographically distributed along the hash table. Okay, so that's the second part, reduce collision. The first part is the hashing function needs to be very, very fast, so we don't want it to be very complex, right?
Okay.
And it's one way. Why do we need it one way? Because if it's two way, what does it mean? If it's two way, look. Let's say if hashing function is two way, what could happen? If a hashing function is two way, what possibly problems can you think of? Right? If hx equals, you get a value v. Yeah. If you can come up with some function fv, and that will give you the x. What does it mean? What does it?
It means that
that's two ways, eh?
yeah.
Right? Then what problem would that give us?
Take so.
No, it means, look, if it's two way, yeah, if it's two way, it means that if this somehow is leaked, the data is leaked here, the hashing location is leaked, then I can deduce the original key will be deduced, right? And there will be a security problem, right? For example, like even the next one you're not sure, but you can try, right? If it's you can deduce it, right? You can deduce it. It means that it's not safe at all. But because generally, right, in database, yeah, when we store the data, when we store the password, right? You know the password is very secret password, right? Usually they don't store the password in a database. In what's database? Database a place to store
They
data.
put it in dots or stars.
Yeah. Look, how do they usually
the I
do?
if you want C, or the I if you don't.
So in database, okay, usually you have a user field, and then you have a password, right?
What is it?
Right? Okay. Password column.
Everyone should all like it.
So let's say, look, Eric,
No.
if your password is 1, 2, 3, 4, okay?
T-shirt.
This is a very simple password. If Ryan, your password is simple.
4, 3, 2, 1.
Okay. So if somehow this information is leaked, right? And people could use your password to do something, yeah, bad, right? We don't want that. We want illegal. We want to prevent that happening. So we don't store the plain password in that. Instead, we store a hashing function, right? We store a hashing function. Usually there's an MD file. We can store MD file or another existing SHA-256. So what it does, this hashing function, what it does is you MD5, look, it give you any password, right? Any password, and then it will give you 32-bit, yeah, 32-bit, something like that, yeah. So look, if MD5, I give a hashing, yeah, hashing. So Eric, you give something hashing AXPTC, right? Or Ryan could be something different, PUTT1, okay? Something I just come up. So
That's
imagine.
the weird one.
Yeah. Imagine this.
Party.
Imagine this information is leaked.
Party. Party.
Okay. What I'm saying is that if this information is leaked,
Party.
can people directly make use of that? Right? No, right? Because
But
look,
maybe.
if H this password, yeah, gives to this column, right? And this.
Is that put one?
Yeah. Okay. I'm just saying that if this data, this encrypted, is hashed, it's not encrypted, it's hashed password, is leaked, then it's less a big problem, right? Because people cannot, this is not a real original password, and people cannot make use of these. These are the encrypted one, and they cannot deduce to the original one, right? Got it? Yeah? Do you understand? Yeah? Okay, so for example, like, look, this hashing function, the collision, what happened? Look, if based on this, if another way, if mommy, but mommy is encrypted the hashing function, okay, so suppose there's a hashing function, it's also AXPTC. So, what does it mean? So, mommy can use the same password or different, but look, your password is 1234. Maybe mommy's password is ABCD, but the hashing function gives ABCD to this AXPTC, yeah? H1234, he also gives the AXPTC. So what does it mean? There's a connection, right? Because the different input, the hash to the same output, the keys. So in theory, right? In theory, mommy could use your username and password. Yeah, to log in, right? But she might not, right? She might not know, right?
Can I?
Yeah, you can do it different, yeah? Do you get it? Yeah. Okay, so today we talk about how to design a hash table.
That's a
Hash
long
table.
time.
No, not a long time. It's very fast. We need a better
Oh my diary.
eraser. Yeah, this is getting bad.
Oh
Okay, so let's say we have a hash table of 10, yeah? Let's say we have a hash table store at most 10 elements. This is 0, 1, 2, 3, 4, 5, 6, 7. Okay. 8, 9, 10, okay? Okay?
Yeah.
So let's make it simple. Our keys are the integers. Okay. So we have let's say we have okay, let's say the key. This is the hash table, yeah? Hash table. This is hash table. So we have a key here. We have a key. The value, this is integer. And let's say if our value is range from 1 to 20. Oh no, let's say from 1 to 20, okay? 1 to 20 inclusive. Yeah, 1 to 20. So how would you map this 1 to 20 to 1 to 10? Right? How would you do it? How would you do it? Which function? Let's come up with a simple hash function. Okay, we haven't talked about a simple hash function. How do we map something into a fixed size table? How do we fix it? Look, define hash. Okay, let's say get key. Okay, and key. This is key. How do we know the size is 10, yeah? We know this table size. Size is 10. Size is 10, okay? We know the size is 10. And how do we map this key? The key, this is the integer, right? So this is the integer, key in. And we want to return to an int, right? Come on. Alright?
Yes.
Okay, so I give you so we want to come up with a function to map the integer to an integer, but with a fixed size.
Yes.
So how can we do it? This table, there are 10 elements in the table, and then our keys are 20, 1 to 20. So I have a few examples, and you tell me what is this function, okay? You guess, okay? Look, 1. If it's 1, I want it to store in 1. If it's 2, I want it to store in 2. If it's 4, I want it to do for 4. No, yet, because if it's 11, I want to store in 1. Is 15, I want it to store in 5. Because they're only from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Okay, there are
But you
11.
put 11.
Okay, let's say 9, 0 to 9. That's 10 elements, okay? So if it's 1, I want to store in 1.
Oh, I know. Like when you did 11, because it goes 9 and then back to the start. And then the 0, 1.
Okay, yeah?
Uh-uh.
Easy, that will be easier. Okay, let's say the key will be
because-
0 as well, and
because-
0 will be 0, okay?
To my program,
Yeah.
instead like 11 is like 9, and then you go back to the start. 10, 11, it's 1. Ta-da!
How about 10? 10. 10.
Huh?
Can you guess where to put the 10?
0.
Yeah, got it. Okay, so
yeah,
what function
my
is that?
calculations was correct.
Then what it is?
Return
Return. So this define and return what?
again.
Return what? Key. What? Two
Key
things.
value.
Key modulus. What's this modulus mean?
Like divide.
Divided by what? By what? Modulus what? Come on. How
10.
10, yes. That's the simplest function. Look, we have a lot of keys to put in the table, right? But we can use these modulus functions to restrict it inside the table, right? Okay. And how about look? What happened? Look. This 1 goes to 1, and 11 goes to 1. So what happened here? Alright, what happened here? 1 goes to 1, so 1 here.
Yep.
So 1, I have a 1. The tuple. Yeah, remember the tuple.
Yeah.
The key of the tuple is the key, the original key. The value is its value. Okay, we can worry about that later. The key value pair, yeah? Because in hash table you have a key value pair, yeah. And then look, 11, 1 goes to 1 here. So you put it at the end. 11 original list is key is 11 and then 1. Okay. The value could be anything. Okay. It doesn't matter. Anything. Got it?
Yes.
Can you see better, please? Can you see better?
We're sitting. Yeah.
Okay. So now today we're going to design this, right? So when we talk about the 3 operation, right? To get a key, to get a value, right? Get a value, to update, yeah, to update a key value pair. And then to remove a key, right? Remove a key. Okay? These 3 operations. To get a key, first of all, we compute this, right? Compute the hash function to tell us where it's going to store. And then we go through this linked list to find out if there's a key in there. If there's a key, we return the value, and the second value in the tuple. Otherwise, if we can't find it, we return the -1 or whatever, or return none, okay?
Yeah.
Update, the same thing. To go through this, if we found it in the linked list, we update the value and return. Otherwise, what do? We append it to the end, the linked list. Am I right?
Yes.
Remove. Again, we find out it's here. And then we find out, okay, 11 is what we want to find, we want to remove. How do we remove a list from a list? How do we remove an item from a list?
You just copy it from and
Okay,
last
look.
note. Yeah. That's a big number.
Okay, 6. Okay,
That's
that's
a big
not okay.
number. 0, 1, 1, 2, 1,
Okay,
3,
no.
1, 4,
No. This is
1,
separate.
5, 1, 6.
0, 1, 2, 3, 4,
Oh.
5, 6. Okay, I want to remove the 3. How do we do?
1, 2, 4, 5.
You copy it. You make it to 6.
Yeah.
Yeah.
And then I remove this
Yeah.
using pop. Remember?
Yeah.
Yeah.
My
Linked list.
calculations.
If we link list, what's the time complexity to remove a link element from a linked list? For us.
From the beginning or end.
Yeah. But look, if a linked list, yeah, we want to remove this, yeah, We go through the element until we found this one we want to remove, yeah. And when we go through the linked list, we know the previous one, right? So all we can do is what? We want to take this out, and we want to modify the previous link to point it to the next one, right? Yeah. Alright.
Yeah.
Instead of copying to the end, because in a linked list, there's no way to get the last value without going one by one, traversing to the end, right? The list provides us this random access because we can just get it by index, calculating the index.
Mm.
Do you understand what I'm saying?
Yeah.
What did I say?
You say, like, rather than just copying it from the other, yeah?
Mm-hmm. This is a list. A linked list is like, look, you're traveling here.
Yeah, and then you travel by a link list. You stole my line.
Yeah?
Yeah.
So, okay, I say it again, okay? So look, this is the list node I want to take it off, right? I found this link node,
And then,
and obviously I know the previous one, yeah, because I come from there. And what did I do? I modify the previous one to point it next to its next one, to the current node's next one, right? So it's slightly different, but a constant term when we modify it. When we know where is the element we want to remove, it's always constant, right? If you are given a number to remove, it's constant term. For example, the list, you just copy the last one and you remove the element for the last one. For the linked list, you know this node is going to take off, right? You modify the previous link, next link to point to the next one, okay? Okay, then let's do it.
yay.
Let's do it. Okay, so let's write it in a class. Okay, object-oriented, we have talked about this before. OOP, yeah? Class. Class. What's class? What's this keyword, class?
A class is where like year 1, year 2, year 3, year 4, year 5.
Class hash table. It's an object-oriented thing, like a person, right? Yeah? The object-oriented, yeah?
Class 1 is the best.
Okay.
Like in cars or anything like that.
Like an object, hash table, so I can use this hash. The class is, you can think of it as a data container, right? A container contains of these data and methods, right? Like a person, class person, right? Class person, and person has the name, age, right? These attributes. And it has methods like talk, sing, dance, right? Got it? Yeah? And then you can use this class to create different objects like
Okay.
Eric equals class, equals person, name, age, right? Something like that. And Ryan equals person, name, age. So in this case, we have created two objects, which is all belongs to the class person, right? So a person, the class is like an object template. Okay. So hash table. So we want to create a hash table. So first of all, we want to initialize it, define the constructor, yeah, to underscore in it. So let's say that we want to store this hash table in minion, right? Or maybe let's say self dot size table size equal maybe. So this, in practically speaking, this number has to be. It's better to be a prime number, so to reduce the collection. So let's say, can you give me a prime number?
9. No.
I'll say
27.
29, okay.
Yeah.
29 or 7, bigger the better. Okay, the biggest,
43.
the biggest prime number I can think of is,
97.
no, 65567.
How do you know that's a prime number, babe?
Okay, wait.
Did you search that up?
Yeah, I searched it out, but this is a prime number. Because I know 65536. This is 2 to the power of 16 maybe? 2 to the power of 16. Yeah? And plus 1. 2 to the power of 16 plus 1. This is the prime number. Got it? Okay, we can check later.
But is it even?
What?
Oh.
It's not even our odd number. This is the 2 to the power of 16. Right? This is obviously not a prime number.
Yeah.
I plus 1, what does it mean?
Yeah.
It's a prime number, right? because you cannot find anything that can be divided by any factors between 1 and itself, right? Okay, so now we want to store this data in the data, save the data. Remember, how do we store this? So each one, look, this table has 65537 slots, slot spaces.
What did you?
Yeah, for each one, Ryan, Eric, for each one is a list, we want to have a linked list, so it will be a list of element, a list of element or linked list. It will be something like that, yeah. To make it simple, we use a list. So here we do what? Save data equals a list. Look, an empty list for underscore in actually an empty list and then for underscore in range what? How many size? So this is save the data, So which is defined here, save the data. Okay? So another instructor is there. Now we want to come up with a simple function. Remember, define get key. Okay, this is get key. What's get key function? If you give a key, and then we need to return a key modulus, right? Modulus save the size, right? Okay, pay attention here. This hash function, this is the simplest hash function. You don't have to. You can write it other ways, or you can provide your hash function. But we generally want hash function to be fast. This is very fast, right? It reduces the collision, maybe or maybe not, right? Yeah. And then the third one, which is what? Avalanche effect, right? Does it? It's not, right? Because look, a different key. Like if I give you a value 10. Okay, if I give you a value 10, in this case, it's stored at location 10. If I give you a key 11, it stores 11. Look, slight changes in the key, and they give the similar values of the hash value, right? Anyway,
yeah.
We don't want that, right? This is okay, but for demonstration purpose, this is okay. Okay, now let's write this. Okay, define. We want to get value, a key, right? So this is the key. We want to get a key. So first of all, we want to do what? Key equals what? Self get key, right? Because we want to find out where it is. And the first step is find out where this key, a key, is in the hash table. So it will be get key, right? We're calling this function self get key, a key. Okay, actually look, because these are actually in Python you have to put the first parameter self. Okay, just remember there will be a first parameter too, because these functions are defined as the class methods. So the first parameter has to be self. What's self?
Self-destruct.
Self means okay. These methods belongs to hash table, so you need to put a hash. Okay, I don't. You just remember that. Okay. Now this key. Now suppose this key is here. Now we want to iterate over this. Yeah. We want to iterate over this to see if there's a key equals to a key, right?
Yeah.
So what kind of search are we performing on the link on here? What kind of search we performing here? We locate this is a key. Linear search, yeah?
Oh.
We just go through one by one, right? There's no better way, right? Because we're not sure. Unless what? Unless you know
It's
this.
super easy.
Unless you know this list is sorted. In that case, we can use what? If the list is sorted, how can we find an element in the sorted list? We can use what kind of algorithm are we using? Remember? The one we always split into half.
Binary.
Binary search, yeah? And
That
that's
was
okay, good job, okay?
good job.
Good job, both of you, good job. Come on, sit there, please.
We're sitting.
So here, we can only use the linear search. So let's go through the for I in what?
Range.
Maybe no, we are not save data dot key, right?
For
So-
I in key.
Self dot data
Self.destruct.
and then this key.
Means you kill yourself.
Okay, so we go through this element and we want to find out if I The first one is the key. The second one is look at the tuple. The first one is the actual a key. So if I0 equal a key, right? Equals to the original key, then we return the value, which is I1 is this value. If after this we haven't found the value, then we return nothing or return -1. Okay, got it? Yeah. Does it make sense? Key. First of all, we want to calculate key is this place, and then here could be Eric, Ryan, or whatever, right? And I need to follow you one by one to find out.
Yeah!
It's actually the first one, the tuple, is the original key, and the value will be the value. Okay.
Yeah.
Okay, so now we have the get, and how about with update? I just change here to update. Okay, update. Update the key, a key and a value, right? We need a value, yeah. var. Okay. First, this is the same. We get a key, right? Okay, so what happened here? We go through the original list. If there's an element, or if this key is already in the element, we just update the value, right? Otherwise, we append it, right? Alright? Do you get my point? So this update function, if the key is already existent in a hash table, we update the value.
Yeah.
If it's not existent, what do? We
We
put
don't care.
no. We put this new thing at the end of this list, right? Got it? Alright.
Yeah.
So look, for I instead of the key, if I0 equals a key, then we don't return it. Instead, what do we do? I1 equal a value. We update it and we return here. Okay, and if at least here, we means that the key is not in the table, so we just append it. So self.data key, right? Dot append. Can you tell me what do I append? What do I append? Append what? A tuple. What tuple? A tuple. Another bracket. What's the key of the tuple? A key, right?
Yeah.
What's the value? Value, yeah. Yeah, you see? If we find it, we change it to the value and we return. If we don't find it, we append one item to the end of the list as a key. Okay. Remove the last one. Remove. How do you remove it? We don't actually need to pass the variable here. We just remove a key. For I, how do we remove? For I, if we found a key, now we found a key, right? Then we need to we need to do what? If we found a key, what should we do? So I, well, so actually so look, I is actually we actually need to copy over, right? So if we need here, for I, let's say range, we're going through the index length, okay? So now here would be I self.data data I0. If I0 is the key, then we copy over the last one, right? Data I, we copy over. How do we copy over? Equals data, okay, data key I, okay, so data key I, first of all key I, key -1, yeah, -1 is the last element, right? And we have to use this, you know, the deep copy and shallow copy.
Yeah, deep copy.
Look.
You copy something from
Which is deep in the sea.
Look, A equals 1, 2, at least. B equals A. Is this a deep copy or shallow copy? A equals 1 to B equals A. Is it a deep copy or shallow copy? Shallow copy, because this B is alias. So if I say B0 equals 10, so what's the value of A0? Look here. B0 is 10. You say it's shallow copy. And what's the value of A0? Come on, can you tell me? A quiz. A is 1, 2, and B equals A. And I said B0 is 10. So what's the value of A0? Come on, you say shallow. What's the shallow? 10. Yeah, exactly. It's a 10 because what it does is here. Look, it's 1, 2, right? A is here, right? A points to here. Look, Eric.
Yeah.
Shadow copy. What does it mean? So B also points to the same place, right? If you change the first element to 10, and you also change the value of A to 10, right?
Yeah.
How about deep copy? How do you do it, Eric?
Yeah.
Deep copy. You can do deep copy. Deep copy is what? Copy. There's a copy package. Copy.deep copy. Yeah. You can do this deep copy, and then you can say
Wow.
B equals copy.deep copy A. Okay, that's the deep copy. Or you can do this. B equals A. Look at.
Oh.
Bracket, and then you put a column.
Dot.
That means the deep copy.
Alien face.
So in this case, if what if I set B0 to 10, and what's the value of A0? Come on.
B0 is to 10.
And what's A0? If it's a deep copy, B is a deep copy of A. Ryan? Eric?
10?
Shadow copy is 10. What's the deep copy?
Oh.
Shadow copy because you're not actually copying. You change one thing, you change for all, right?
2.
1, 2, and I change the first element to 10. So what's the A0? What's the A0 here? Is it changed?
2.
Is it changed?
1, 2.
Yeah, 1, 2. It's not changing. A0 is 1. It's not changed, right? Because B is totally a deep copy of A. Changing everything to B doesn't affect A, right? Yeah? It's like you, Eric, you are Ryan, you are a clone of Eric, right?
Yeah.
I'm a small clone of
Yeah,
Eric.
small clone. So does it make sense? Eh? If you anything you finish your homework does not mean that Eric finishes his homework, right? You are two different, independent, right? Got it? Make sense? Okay, so we are a little bit far away. So look, we did copy and then we copy over the last one. So what's the next one? If I want to delete it, data key
Key is a B.
data key, and we want to remove the last one, which is use word method. Come on, dot pop. Yeah, we remove the last one. This is constant term. So look, if the key, we go through this linked list or list, and we find out if there is a key, and then we remove it, and then we return. Yeah, we just return because we just remove one. That's it. And if there is no key, and then we just ignore it, and it will be here. And we can say, okay, raise exception here. Yeah, raise exception. Yeah, raise exception. Key not found. Okay, whatever. Right. Okay. What have you learned so far today?
Hash. Hash table.
What are we trying to do here?
Hash table.
Design a hash table,
Yeah.
right? So in a hash table, what's the most important thing you can think of?
Deep clone.
No? What's the most important thing? What's the most important thing? What's this?
It doesn't change. It
What's
doesn't
this?
change. Key.
Hash function. Hash function allows us to, because this is important. If given this input key, you want to find out where to put it, right? We want it to be as far as possible, right? So they don't collide each other.
Yeah.
So that will give us the time complexity, how quick it is. What? 3 operations.
Beep, 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 beep.
O1, and O1, all O1, right? This is the most biggest advantage of using hash table, right? Got it? So, just one last question. If a hash table is fixed size, okay, let's say it's fixed size, and if there are too many elements coming through the hash table, what could happen? The performance of the hash table will be decreased or increased. It will be decreased. If there are too many elements in the hash table, can you imagine the performance to look up, to remove, to update would be slower or faster? Come on, be confident. The more elements in the hash table, there will be more chance of what?
Faster.
More chance of what? Come on. Your fixed size. Come on. This is a hash table. Only 3 people. If your friend all come in, what happen? Too crowded. What happen in hash table? It'll be too crowded as well.
slow.
It'll be slow because the hashing
Because
function.
you get loads of traffic.
Lots of traffic because of the collision. Yeah, what did we talk about collision? Because look, if there are too many elements and there will be all filled, yeah, the table will be much filled. And if any more comes in, what will happen? It has to be put it in the hash table, right? So it could be somewhere in the linked list, right? Alright? Does it make sense, right? Look at me.
Yeah.
So look, if this hash table is pretty much filled, then the operation to search could be very slow because look, this bit could be very large list. Yeah, this could be a very large list. Even you separate using the hash key, but you still have to do this in linear time. Yeah, to look for these elements in the linked list. So that will slow you down. We don't want that happen, right? That's why we can have a bigger hash table. Yeah, bigger hash table, a better hash key to distribute the keys evenly everywhere in the table, right? So that will give us the O1 constant, nearly in practically very fast O1 constant time. Okay? Yeah, are you still with me? Okay. Any questions so far?
Yeah.
Any questions so far? Any question? No? Any question? Okay. Okay,
Why
let's
is
see.
a hash table a type of class?
Yeah, the hash table. Look, this is a hash table. Define a hash table. Remember, hash table is data structure, the notebook thingy we talk about, right? Remember yesterday we talked about this dictionary, yeah? Dictionary, yeah? Default dictionary, yeah? So I have a notebook. I said what? Key value pair. Key value pair. Ryan, key equals Ryan, value equals 8, right?
I'm not 8.
9. No, 7. Okay. And I put it over, and then later people ask, how old is Ryan? I look it up. Okay, look it up a key. Very fast, O1 constant time. Okay, and retrieve the value, which is 8.
But you need to flick on the right page.
No. That's the beauty of hash table.
Huh?
A key, get key. It tells me, okay, it tells me which page it is. Get key.
Oh.
That's why it's so fast. Okay, you can, yeah, good point. You can think of these dots as different pages. Yeah, different pages. Got it? Okay, that's a good way of thinking. Very well done. I haven't thought it that way, but it's a very excellent demonstration of how this is different page. A book. This is a book. And page 1, page 2, page 3, page 4. Right? A key, get key. Eric. Okay? It tells me, okay, it's in page 3. Right? So I turn to page 3. This is instant time. And I see, okay, Eric, key Eric, value 9. Retrieve it very fast. Then if Ryan, the key, is also on page 3, what happened? If there are too many items on page 3, what happened? You still have to look through this.
Owen!
Yeah? Do you get it? You still have to read through the page 3, right? To find out where is Eric, right? So that will slow you down.
Ryan.
Okay, Ryan, that will slow you down. Am I right? Does it make sense?
Yeah.
You now understand the concept of this, yeah? Hash table, yeah? Yeah? So how do we make it fast? First of all, there are a few things to make it fast. First of all, you buy a bigger book, so lots of pages, so you don't have collisions. Yeah, the bigger page, less collision, right? Alright, yeah, yeah. Got it? Lots of pages. Yeah. Okay. That's it for today. Good job.
Yay!
Bye bye.
Yay.